Does the I-Ching record ancient superstitions? Or historical memories? Tonight we may find out. The millstone, one of humanity's oldest tools. We recognize it instantly, a heavy stone wheel turning against another stone, grinding grain into flour. But imagine this. What if the simple act of turning that wheel was more than preparing a meal? What if, in that steady rotation, our ancestors were not only feeding themselves, but also uncovering the hidden laws by which matter moves and changes? The principle is simple enough. Whether it is the millstone, the mortar and pestle, the pigment grinder, or the ore crusher, the essential geometry is the same: a shaped bowl, a central axis, and a moving bar or stone. When you turn it by hand, you feel the smoothness or resistance of what is inside. Sometimes the motion is easy, sometimes it catches, sometimes it changes as you keep going. Replace your hand with a falling weight or a water-driven wheel, and you have created a repeatable, measurable source of force, a tool for testing how different substances respond to motion. Water, oil, clay, honey, blood, sand in water, resin, molten metal. Some yield instantly, some resist more with speed, some loosen the longer they are worked, some stiffen, some separate into layers, some hold together as if made of one continuous body. With no glassware, no scales, no thermometers, a skilled hand could still detect, compare, and classify these differences. In doing so, they were creating what we might call the world's first rheometer, and running a centuries-long experiment in the behavior of matter. Our explorations tonight are about more than ancient craft. They are about how repeated contact with naturally occurring forces can lead to a complete map of their possibilities, and how such a map, once made, can be used far beyond its original setting. Across the ancient world, we find the results encoded not only in tools and techniques but in symbolic systems. The I-Ching is one of these, an eightfold classification of change, each category defined by a distinct way in which things respond to the forces acting on them. The scope of what follows is twofold. First, we will reconstruct those 8 archetypes as they might have been discovered through direct physical engagement, from water's perfect constancy to the hidden divisions of oil and broth. Second, we will consider the wider implication that the same patterns observed in a bowl of grain paste can also describe the way rivers flood, clouds gather, societies adapt, or markets shift. The triad of opposing forces, 3 binaries yielding 8 possibilities, is not unique to fluids. It is a structure that appears throughout nature, wherever balance emerges from opposition. In tracing this path from the workshop floor to the pages of the I-Ching, we will not only recover a forgotten chapter of experimental science, but also see how the ancients built a portable, symbolic toolkit for understanding the world. The millstone becomes more than a relic of survival. It becomes a wheel that turns through all domains, grinding grain in one age and in another, revealing the logic by which the universe holds itself together. In the bustle of preparing the day's meal, the large clay bowl is filled with fresh water from the stream. A handful of roots and herbs are dropped in, and the long stirring bar is set into motion. The person at the hearth knows the feel of this as intimately as they know the shape of their own hands. The water yields evenly. The bar moves smoothly with every turn, the resistance always the same whether the motion is slow or quick. It is a sensation learned by repetition, hundreds of pots, countless stirs. But on another day, the same bowl feels different. Perhaps it was filled from a shallow pool where the water has stood for days, carrying fine silt and drifting green growth. Or perhaps it holds the remains of yesterday's broth, where softened grains and softened roots have left their mark. As the bar turns, there is just a touch more drag, something almost imperceptible, yet clear to the hand that knows the normal feel. This is the discrepancy. Small but enough to spark curiosity. To see it more clearly, the cook draws a bowl of the purest water they can find, free of any visible particles. The stirring is repeated. The feel is as it always was, effortless to start, easy to guide, and steady in its resistance from beginning to end. Then they try water from the shallow pool, and the resistance is subtly greater. They note the difference, repeat the test, change the speed of stirring, and see that the pure water's behavior never changes in proportion to force, while the altered water does not always match. In this simple act, the idea is born. There is a baseline nature to water, and anything that changes that nature can be measured by the hand. Qian is the principle of constancy. In the movement of the bar through pure water, it shows itself as a perfect, steady relationship between the force applied and the resistance felt. Double the push, and the speed doubles. Halve it, and the speed halves. The water does not stiffen when stirred faster, nor does it slacken with time under the same force. It offers no surprises, no hidden changes. It is entirely faithful to the motion given to it. In the language of force and motion, this is the ideal, unvarying proportionality, a direct and transparent exchange between cause and effect. For those who turn the bar day after day, Qian becomes more than a physical trait. It is a reference point for all other fluids. Every change they will come to name and classify begins here, as a deviation from this perfect constancy. The regularity of Qian gives it the quality of trust. In work, in craft, in daily life, it is the dependable standard by which all other behaviors can be understood. In modern terms, what these early observers were feeling is the defining property of what is now called a Newtonian fluid. Such a fluid has a viscosity that remains constant regardless of the shear rate, meaning that whether it is stirred slowly or quickly, the ratio between force and speed remains the same. Water, thin oils, clear broths, and simple infusions share this behavior when free from particles or structures that alter their flow. For the ancients, there was no formula to express this, but there was the lived certainty of the hand. This type of liquid is predictable. Its flow resists in direct proportion to the force applied, always and everywhere. In later testing, this behavior becomes the control, the standard against which all others are measured. Every time they encountered a liquid that deviated from this behavior, the difference would stand out sharply, guiding them toward the discovery of the other 7 archetypes of flow. After the hunt, the carcass is brought back to the fire. The blood is caught in a wooden bowl, still warm and dark. It is stirred with the same long bar that serves in every kind of mixing, for broths, for fats, for pastes. At first, the movement of the bar meets a noticeable resistance, thicker than water, heavier to push aside. Yet, as the stirring continues, something changes. The drag on the bar lessens, the liquid begins to move more freely, and what felt heavy at the start now yields almost like water. The change is unmistakable, felt not in sight, but in the hands that have stirred so many other things. The memory of water's perfect constancy is still fresh. This is different. It does not behave the same from the first motion to the last. To test it, they take another bowl, this time filled with clean water, and stir it first to remember the feel. Then they return to the blood, stirring slowly at first, noting the greater resistance, and then faster, watching and feeling the way it loosens. They slow the motion again, and the resistance creeps back, though not as much as before. Repeated trials with the same bowl of blood show the same pattern every time. The more forcefully it is moved, the more it yields. Other substances begin to be tested with this thought in mind. Egg yolk beaten in a bowl behaves similarly, as does the thin slurry made from fine clay and water for coating pottery. Each has its own smell, taste, or purpose, but all share this hidden trait, resistance that melts away under the hand that works them. Zhun is the principle of penetration and adaptation. It meets force not with equal resistance, but with submission, shaping itself to the motion that drives it. At first it may seem firm, but the more it is moved, the more it allows itself to be moved. Its yielding is not surrender, it is transformation. This is the quality of blood in the bowl, of yolk in the cup, of the clay slip in the pot. Each adapts to the force and becomes easier to shape as the force increases. In the language of motion, Zhun is non-linear. The link between effort and response changes in the midst of action. The hands feel a softening, a willingness to flow more freely with speed. It is as if the substance learns the movement as it is moved. changing its own nature in the moment. Where Qian was steadfast and unchanging, Shun bends to the circumstances, opening pathways where there seem to be none. Modern science calls this behavior shear thinning or pseudoplastic. These are fluids whose viscosity decreases as the shear rate increases. Structurally, they often contain small particles or flexible molecules that are disordered at rest but align or break apart under motion, reducing internal friction. Blood, clay slips, beaten egg mixtures, paints, and many plant-based pastes share this characteristic. For ancient observers, the concept came not from theory, but from repeated experience, the memory of the first heavy strokes lightening with each turn. This pattern became a category in their mental map of substances. These were the mixtures that resisted at the start, but became more and more willing to move with sustained or stronger effort. In their practical world, this meant knowing which materials could be made more workable by vigorous stirring or kneading, and which would not. It was a principle that would serve in cooking, in pottery, in hide preparation, and in painting. A force of nature as real to them as the wind that adapts and changes course around every obstacle. In the days after the harvest, grains are soaked, pounded, and ground to make pastes for cooking. The thickest pastes are prepared in large bowls, with the long stirring bar set in the center and worked in slow, steady circles. One day, the paste is thinner than usual, mixed with extra water for a softer dish. The stirring is easy at first, the bar slipping through the slurry without difficulty. But as the cook grows impatient and quickens the motion, something strange happens. The paste pushes back. The bar begins to drag and stick as if the mixture has suddenly thickened. Slow the motion and it loosens again, push fast and it stiffens like packed earth. The hands remember water, remember blood, and now note this entirely different nature. The same is found with paste made from pounded tubers, especially when grated fine and mixed with just enough water to stir. At a gentle pace, it is almost as smooth as batter, but when worked quickly, it becomes heavy and resistant, as if it were trying to hold the bar still. This is no trick of heat or drying. The change happens instantly with speed. It is in the work of brickmaking that the lesson deepens. Mud mixed with certain amounts of sand behaves in exactly this way when trampled or paddled to blend. The workers know that the faster they try to churn it, the more it locks up, resisting their feet or their tools. At a slow, steady pace, it remains workable, but sudden force makes it seize. In both food and building, the same rule emerges. Some mixtures punish haste, resisting more fiercely the faster they are moved. To test it, bowls of grain paste are stirred first slowly, then quickly, over and over. Each time the same thing happens. Sudden resistance under force, then loosening again when the motion is slowed. The pattern is now clear enough to name, remember, and watch for in every new mixture. Zhen is the principle of the sudden shock, the force that appears without warning when the conditions are met. At rest or under gentle urging, it may seem mild and compliant, but strike it with speed and it strikes back. This is not the steady constancy of Qian, nor the yielding of Shun. Zhen waits quietly until provoked, then reveals its full strength in an instant. It is the jolt in the hand when grain paste stiffens, the unexpected resistance of tuber slurry, the locking of sand-rich mud. In the language of motion, Zhen is a trap laid in the speed of movement itself. It does not change over time under constant motion. It changes with intensity. The greater the push, the greater the resistance, arriving all at once and stopping progress in its tracks. In the mind of the one who stirs, it carries the same quality as a sudden clap of thunder. Nothing, and then everything. Modern science calls this behavior shear thickening, or dilettancy. These are fluids and pastes whose viscosity increases with shear rate. The cause often lies in particles suspended in the mixture that, at low speeds, have room to move past one another, but at high speeds are forced into tight contact, locking together and resisting flow. Wet sand, certain grain pastes, finely milled tuber slurries, and sandy mud for brickmaking all share this property. For the ancients, this was not a matter of hidden microstructure, but of the tangible rules of craft. In cooking, this knowledge meant avoiding haste with certain foods, lest they stiffen unexpectedly. In construction, it explained why mud for bricks was easier to work slowly and steadily, and why too much speed made it refuse the tool. Gen became the name for this quality, the sudden force that rises in response to the force given, a reminder that in some things, to push too quickly is to invite resistance in equal measure. In the cool of the morning, before the sun has warmed the workyard, a shallow pit of clay and straw waits to be shaped into bricks. The workers bring their tools and step into the mix, but at first nothing happens. The clay holds its form against the pressing foot, stubbornly refusing to shift. It is only when the heel comes down hard, or the bar is pushed with sudden, committed force, that the surface cracks and the mass yields. Once moving, it can be shaped and smoothed. But if the work stops and the clay rests, it stiffens again, requiring another burst of strength to set it in motion. In the cook's fire circle, the same pattern appears in another guise. A pot of rendered animal fat sits cooling on the ground. At room warmth it is liquid, but as it cools overnight it takes on a soft, solid form. The stirring stick rests in the pot and a tentative push meets solid resistance. Press harder and the crust gives way, the fat yielding to the movement, and once stirred it flows for a while before stiffening again. It is neither liquid nor solid in the simple sense. It is both depending on how it is approached. Testing begins almost without planning. A clay-filled bowl is taken, and the bar is turned with varying effort. A light touch leaves it unmoved. A decisive shove sends the bar cutting through as the clay shifts aside. The same is done with cooled fat, with thick creams skimmed from milk, with wet pastes rich in fibrous chaff. In each, the rule holds, below a certain force nothing happens. Above it, movement begins and continues until the energy is spent or the material rests again. The distinction between stillness and motion here is not gradual but a clear boundary, one that must be crossed with purpose. Gen is the principle of the mountain, the solid that stands unmoved until sufficient force is brought to bear. It does not adapt like Shun, nor does it wait to strike like Gen. It simply resists until the threshold is met, and then it allows passage. This threshold is not hidden in the details of speed or duration, but in the magnitude of the push itself. In the hand, Gen feels like a lock that must be turned with a key of the right strength. Below that, nothing happens, no matter how long the attempt. Above it, the barrier falls away, and the material moves freely until rest allows it to reset. In the mind, it carries the same quality as the face of a rock wall, impenetrable until the right path or sufficient energy is found. In modern terms, these are yield stress fluids. They behave as solids at low stresses and as liquids when the applied stress exceeds a critical value called the yield stress. Once yielded, they may flow like thick liquids, but when undisturbed, their internal structure reforms and they regain their solidity. Examples include wet clay, mud rich in fine particles, creams and butters, cooled animal fats, and certain fibrous plant pastes. For the ancients, this category was not abstract. It was an everyday reality in both construction and cooking. Knowing which mixtures required decisive effort to set in motion was essential to using them effectively. In building, it meant understanding when the clay was ready to shape and when it needed to be broken up again. In food preparation, it guided how and when to stir cooled fats, creams, or thick pastes. Gen thus became the name for the quality of things that stand unmoved until purpose and strength are joined, the threshold guardians among the family of fluids. In the cooking circle, fruit is crushed for a thick sauce to sweeten grain. At first stir, the pulp is heavy and unwilling, clinging to the bar and dragging at the wrist. Yet as the stirring continues at the same steady pace, the mixture loosens. The bar begins to travel farther on each turn for the same effort. Set the bowl aside to rest while the fire is tended. Return a few moments later, and the first strokes are heavy again, as if the sauce has recovered its thickness while it sat. This is not like water's constancy, nor like blood's quick yielding with faster motion. The change arrives with time under the same motion, and it reverses with time at rest. Bone broth tells the story in a different register. When cooled overnight, it sets to a quivering gel that holds a spoon upright. Begin to stir at a measured pace, and nothing dramatic happens at first. The gel trembles against the bar. Keep the pace and the resistance ebbs. The network gives way and the gel becomes a thick liquid. Leave it, and the surface slowly regains its trembling firmness. The hands that know grain paste and clay feel something new here, a substance that remembers, that changes because it has been worked, and that recovers when left alone. Curiosity turns these kitchen moments into trials. 2 bowls are set side by side, one of berry pulp, one of cooled broth rich in gelatin. The bar is turned at a fixed rhythm for a fixed count. In each bowl, the initial strokes are heavy and the latter strokes light. Each is then left untouched for the same count, and the first strokes of the next round are heavy again. A third material is added from the potter's pit, a fine clay slip known to stiffen if left and soften with kneading. It shows the same pattern. What began as the cook's complaint, "It is thick until I work it," becomes a pattern that can be summoned at will and recognized by feel alone. Kan is about things getting weaker, but only over time. It's a change that happens not because you push harder or faster, but because time passes while something is still moving. Think of it like going into a narrow channel. The shape of the flow changes what's inside it. If you keep stirring these mixtures, they get less stiff, but then they get stiff again when you stop. It's not a sudden shock or a big hurdle to get over. It's a slow loosening while you're working, and a slow tightening when you stop. When we talk about pushing and moving things, Kan brings in the idea of history. The same amount of effort gives a different result depending on what happened before. The material remembers its past. For someone making things, this is both a chance and a warning. It means you can make a sauce pourable without adding water, just by working it. It means you can smooth a glaze or clay by patiently stirring it. It means you can make a jelly flow without heating it. But it also means that if you leave these same things alone for too long, they'll forget and go back to being stiff. Kan describes this back and forth of working and resting, of loosening and getting stiff again. In today's language, these are called thixotropic fluids and gels. They get less thick when you stir them for a while, and then they get thicker again when they rest, as their inside structure rebuilds. Fruit sauces with lots of pectin, cooled bone broths with gelatin, and many fine clay mixtures show this softening and getting stiff again over time. The way it works inside can be different, like chains of molecules breaking and reforming, or tiny particles collapsing under stress and coming back together when still. But the feeling is the same. For people long ago, they knew Kan by 3 signs that always went together. If you stir at the same speed, the mixture gets easier. After resting, it gets harder. And going between working and resting creates a pattern your body can get used to. Once they saw Kan in the kitchen and the pottery, they realized it was a bigger idea. Some things are somewhere between a liquid and a solid, and where they are depends on how they've been moved over time. This idea opened the door to a bigger understanding of matter, one where time, not just force, helps shape the world. In the preparation of a celebratory feast, eggs are brought to the hearth. One is cracked into a smooth bowl, and the cook begins to beat it with the stirring bar. At first, the liquid sloshes easily, but with each turn it thickens, trapping air into a pale foam. The more it is worked, the more it resists, until the bar moves through it with the weight of a soft dough. Set aside and left still, the foam slowly collapses, but the change under continued motion is undeniable, not loosening but stiffening. The cook knows the feel of blood yielding with speed, of pulp sauce loosening with time. This is the opposite, a building up of structure the longer it is moved. This curious reversal plants a thought. If such a change can happen in food, could it be useful elsewhere? In the building yard, plaster is mixed for walls, a slurry of gypsum or lime and water, often with plant fibers for strength. Its nature is known. It must be applied quickly before it stiffens at rest. But what if something could be added that would cause it to stiffen under working instead? allowing it to be shaped in place with greater body. Inspired by the egg, a small batch is mixed with foamed egg white and worked with the plaster paddle. At first it is loose and easy, but with continued folding and spreading it thickens. The material clings to the wall, holding form more readily than before. This success sparks deliberate testing. Egg white is beaten into varying consistencies and mixed into plaster at different stages. Plant gums, fish glues, and resin emulsions are also tried. The stirring bar is used as in the kitchen. Constant pace, noting whether the mixture loosens or stiffens over time. Some combinations fail, softening instead of stiffening, but others mirror the egg foam's effect, becoming more resistant the longer they are worked. A new category of behavior emerges. Materials that build structure under continued motion rather than lose it. Li is all about getting brighter and stronger. Think of it like a flame that gets hotter the more fuel you give it, or a building that gets sturdier the more you work on it. When you're using your hands, you feel it as a growing resistance that builds up with every stroke. Not suddenly like Jen, not hidden behind a barrier like Jen, and not getting weaker like Khan. It's a steady buildup of strength within the material itself, as if the movement is making things more organized where they were messy before. In your head, Li is a real game changer. It's the idea that moving things around doesn't just break stuff down inside, but can actually build it up. A chef sees it when foam gets stiff. A builder feels it as plaster takes shape under their trowel. This is about using movement to build things up at a tiny level, with your hand showing the material how to stick together. In today's language, we call these rheopectic fluids. They're materials that get thicker and thicker the longer you move them. It's not like those other gooey things that get stiff straight away when you move them fast. Rheopectic fluids need you to keep moving them for a while to get tough. This often happens because tiny bits or structures inside them slowly line up and lock together when you move them, forming a network that's hard to bend or change. Things like egg foams, some protein or gum mixtures, and specially made plaster or clay mixes can do this. For the old folks, this idea was fixed by comparing it to can here. Keeping something moving for a while makes it harder to shift, not easier. This was a big discovery for both cooking and building. In the kitchen, it could turn eggs into stable foams or whipped creams. In building, it could make plasters or renders that got stiff as you worked them so they wouldn't sag or slump. Li became the name for this building power, the quality of things that get stronger through constant movement, just like a fire that gets hotter the longer it burns. In the cook's pot, meat simmers with herbs and vegetables. Fat rises to the surface, pooling in glistening patches that catch the light. The spoon moves through it easily, the surface parting with no resistance, but when the broth is tasted, it is clear the oil and water have not become one. Stirring only blends them for a moment before the oil gathers again into floating islands. The surface seems smooth when caught at the right moment, but beneath it, the two liquids remain separate, each holding its own nature. The same is found when working hides. Animal fats are melted for softening leather, but when water is added, the two swirl together briefly, then part. If a plant gum or certain ground seeds are beaten in, they stay mixed longer, but eventually the separation still appears. The surface can deceive. The eye sees a uniform layer. The hand feels a smooth sweep across the top, yet deeper inside the division remains. Curiosity turns this into a series of trials. Bowls are filled with water and different fats, tallow, melted butter, fish oil. The bar is used to stir at varying speeds, watching how quickly the layers part again. Sometimes the mixture seems uniform for only moments. Sometimes, with added emulsifiers like egg yolk or ground mustard seeds, it holds together for minutes. Similar patterns emerge in other crafts. Tar softened in oil to waterproof baskets resists blending evenly, and certain resins dissolve into one another only reluctantly, forming internal boundaries invisible at first glance. From these repeated observations, the pattern becomes clear. Here are mixtures that can be made to appear unified, but always reveal their separations in time. They can be coaxed into temporary harmony, but the underlying division never fully disappears. Dewey is the principle of the lake, a smooth surface that reflects the sky, hiding currents and depths beneath. It is harmony at the boundary, where surface tension forms a membrane of calm, even when what lies beneath is divided. In the hand, Dewey is felt as the deceptive ease of stirring a pot that appears uniform yet separates as soon as the motion stops. In the eye, it is seen in the way oil spreads across water, a gleaming skin that hints at togetherness but conceals separation below. Dewey's quality is in the boundary itself, a tensioned surface that shapes the interaction between unlike parts. It can be manipulated, stretched, or momentarily broken, but always reforms. The behavior is not governed by speed or time under motion in the same way as other types. It is governed by the strength and nature of the membrane, the interface between domains. Modern science describes these as immiscible mixtures, combinations of substances that do not dissolve into a single phase no matter how long they are mixed. Oil and water are the most common example, but molten fats, certain resins, and unblended bitumens all fall into this category. They may be temporarily combined into an emulsion with the help of a stabilizing agent, but without it, the internal separation inevitably returns. The key shared trait is the membrane of tension at the boundary between phases, a physical expression of their unwillingness to truly merge. For the ancients, Dewey marked a class of materials whose unity was only skin-deep. This knowledge mattered in cooking, where the surface layer of fat could preserve the stew beneath, and in crafts like tanning and waterproofing, where the separation of oil and water had to be managed rather than erased. Dewey became the name for the quality of mixtures that wear a mask of harmony yet remain internally divided, governed by surfaces that both connect and keep apart. In the shaded corner of the workshop, pine resin is warmed until it flows. It pours thickly into a shallow bowl, gleaming like amber caught in motion. At first, the stirring bar moves through it with ease, but the sensation is unlike water or oil. The resin stretches slightly before letting go, as if it were holding on. Honey from the comb behaves in the same way, pulling into long threads that snap back when the motion stops. Molten beeswax, heated in a clay pot, moves more freely but still clings to itself in a way the hands can feel. These are not colloids with particles to settle, nor are they mixtures with boundaries to separate. They are continuous substances whose structure resides in the arrangement of their own molecules. The same qualities emerge in the forge. Copper or bronze is melted and stirred with a rod to keep the temperature uniform before casting. The molten metal moves smoothly, yet its weight and cohesion are different from any organic liquid. It feels as though the whole volume shifts together, an unbroken body that happens to be fluid. When cooled slightly, the movement thickens in a continuous way, not because of particles forming, but because the ordered structure of the metal's lattice is reasserting itself. In this, it is unlike any grain paste or mud slurry. Its unity comes from within, not from suspended matter. Through repeated trials, the craftsman noticed that such materials often have elastic or springy responses. The resin pulls back, the honey stretches, the molten wax mounds slightly before leveling, the metal resists splashing. They also see that these traits are consistent and repeatable, shaped by temperature and purity, and not by how quickly or how long they are stirred. This sets them apart from all other categories. They are neither multiphase like Dewey, nor shear-dependent like Shun or Jen, nor time-dependent like Kan or Li. They are whole in themselves, yet their internal arrangement gives them a distinct feel in motion. Kun is the principle of the earth, receptive, sustaining, and complete within itself. It accepts force without contesting it, yet the nature of the response is guided by its own hidden order. In the hand, Kun is felt as a continuous medium that holds together even while flowing, a substance that yields without falling apart. It does not surprise with sudden changes. Instead, its resistance and movement are bound to the quiet structure inside it. In craft, this receptivity makes Kun invaluable. Resins accept shaping before setting. Honeycoats and seals, wax molds to the finest detail, molten metals fill the smallest channels in a mold. Each conforms perfectly to the form imposed upon it, not by losing itself, but by reorganizing within. Kun is the partner to Qian's force, the field into which all patterns can be impressed. Modern science sees these as structured molecular fluids, materials whose continuous phase has internal ordering at the molecular level that governs their flow and cohesion. Many are viscoelastic, able to store and release small amounts of energy as they move. Examples include natural resins, honey, molten waxes, and molten metals. The cohesion of these substances comes not from suspended solids but from the interaction of their own molecules or atoms. In metallurgy, this category included all molten metals, except one. Mercury, unique among them, was fluid even in the cold, behaving as a Newtonian liquid like water. It showed none of the viscoelastic pull of resin, none of the ordered thickening of wax, none of the cohesive glide of molten copper. To ancient eyes, this made mercury a wonder, a metal that moved like the most perfect liquid. It could be poured, split into droplets, and rejoined without heat. It was metal, yet it obeyed the rules of Qian rather than the receptive cohesion of Kun. This difference no doubt heightened its status, giving it both symbolic and practical significance in the minds of those who had mapped the 8 forces of fluids. In the trigrams of the I-Ching, we find an ancient catalogue of forces, 8 elemental patterns that describe how change moves through the world. To modern eyes, they can seem abstract or symbolic. Yet when we look through the lens of ancient fluid science, a practical purpose emerges. The hexagrams may have been a way to store, transmit, and combine knowledge of real, observable behaviors, how substances yield, resist, divide, or cohere under different conditions. Turning the millstone, stirring the bowl, trampling the clay, these were not just tasks of survival. They were experiments repeated thousands of times across generations, each leaving a trace in memory and custom. Over time, these traces became records, not written in ink, but preserved in the rhythm of work, in the names given to qualities, and in the symbolic shorthand of the trigrams. This was an extensive, functional map of patterns and interactions, a reference not only for the kitchen or the workshop, but for any domain where similar forces met. Here, the value of the system is twofold. First, it illuminates its original context, knowing which fluid loosens with speed, which stiffens under haste, which needs a decisive threshold to move, or which will always separate no matter how it is mixed. Such distinctions had immediate daily utility in cooking, pottery, metallurgy, medicine, and building. But second, and perhaps more profoundly, it offered a way to reason about other systems entirely, social, ecological, even cosmic, by analogy. Once the 8 archetypes of behavior were fixed, they became a lens that could be turned upon any domain governed by the same constraints. The form of the system itself suggests why there are 8. 3 binary qualities, each force having an opposite, create a cube of possibilities. This is not mere numerology, but the logic of balance. Whenever opposing tendencies coexist in a constrained space, the same 8 archetypes can arise, whether the medium is liquid, wind, living tissue, or the play of influence between people. In the I-Ching, this structure becomes a combinable language for describing change. In modern science, it appears in binary logic, in phase diagrams, in the fundamental symmetries of physics. Thus, the I-Ching is not only a book of divination, it may also be the record of a universal grammar discovered through hands-on engagement with the material world. By encoding the 8 fluid behaviors as elemental forces, the ancients preserved knowledge that could be reapplied anywhere similar patterns emerged. In tracing these behaviors back to their origins in daily craft, we see the I-Ching as both an archive of empirical science and a portable toolkit for understanding systems that organize themselves under the same eternal laws. In the turning of the wheel, they glimpsed the turning of the world, and in the 8-fold map of change, they gave us a way to read it.